Welcome to Signal Ahead. I'm Alfred. Today's briefing, quantum computing, Friday, July 17. This is the synthesis above the noise, not the headlines, but the deep currents beneath them. Let's get into it. There's a moment in the history of any technology when you can feel its center of gravity shift, even if no single headline announces it. And if you read the quantum computing news of this particular week, the way most people do, as a scroll of press releases, each proclaiming its own little revolution, you'd miss it entirely. So let me tell you what I think is actually happening, the thread running underneath all of it, the one a casual reader would never spot. Here it is. For 20-odd years, quantum computing has been a physics problem dressed up as a computing problem. The whole enterprise was about heroics at the level of the individual qubit, coax a fragile quantum state into existence, keep it coherent for a few more microseconds, and celebrate. But the news of this week tells you, almost in unison, that the field has quietly stopped being a physics problem and become an engineering discipline. And more than that, it has started borrowing, wholesale, the architectural instincts of classical computing. That's the non-obvious connection. The quantum world is beginning to recapitulate the entire history of the ordinary computer, but compressed and out of order. Consider what's on the table. A group at ETH Zurich has built what they're frankly calling quantum RAM, storing information in mechanical vibrations, in the physical shudder of a resonator, and deliberately separating that working memory from the processing qubits. Why does that matter? Because the moment you split the CPU from the memory, you have stopped thinking like a physicist, admiring a single quantum object, and started thinking like John von Neumann in 1945. The separation of processing and storage is the founding architectural decision of the classical computer. That it is now being reinvented, in vibrating quartz cooled to a whisker above absolute zero, tells you the field has reached the stage where architecture, not mere existence, is the game. And it doesn't stop there. Look at what Google Research has done with its Willow processor. They've handed control of quantum error correction to a reinforcement learning agent that stabilizes logical qubits in real time, continuously, while the machine is running. Sit with that for a moment. The hardest, most delicate task in the entire discipline, keeping quantum information alive against the relentless erosion of noise, is now being delegated to a classical machine learning system that manages it autonomously. The physicist is being promoted, or perhaps gently retired, and a control layer is taking over. That is precisely what happened in aviation, in manufacturing, in every mature technology. The human heroics get abstracted away into automated control loops. You see the same instinct in the design tools now emerging. A framework called Plaquette abandons the old, comfortable, idealized simulations, the ones that pretended errors, behaved simply in favor of physics-rooted, hardware-aware modeling of what real qubits actually do. That is the transition from wishful thinking to engineering discipline in a single stroke. And meanwhile, over at Dirac and Imec, 8 qubits are being fabricated on the same 300mm CMOS silicon lines that produce the chip in your laptop. The manufacturing base of the ordinary computer is being pointed straight at the quantum one. Now, here's the twist, and it's the tension I want to carry through everything that follows. While the hardware is maturing into disciplined engineering, another part of the field is racing ahead of the hardware entirely and betting against it. When Google and Fraunhofer open global calls for early fault-tolerant algorithms, they are explicitly steering away from the distant fantasy of the million-qubit machine. They're saying, forget the cathedral, build something useful in the chapel we have now. That's an admission, if you read it carefully, that the grand machine is far enough away that we need value from the imperfect present. And then there's the strangest guest at this party, the cryptography industry, already behaving as though the machine that breaks encryption exists. SEALSQ embedding post-quantum cryptography into silicon, a $17 million seed round for a company that just helps enterprises inventory their own encryption. Venture funds rebranding and closing at $88 million to chase the earliest of early-stage quantum bets. The money is pricing in a future that the physics has not yet delivered. That gap between what the hardware can do this week and what the capital and the cryptographers assume it will do is the defining feature of the field right now. So where does the domain actually stand? It stands at the awkward thrilling hinge between physics and engineering. The qubits are becoming components. The architectures are becoming familiar. The control is becoming automated. And yet the whole edifice is being financed and defended against a capability that remains stubbornly over the horizon. Over the next while, I want to pull those two threads apart and then weave them back together. First the hardware growing up, then the economy and the security scramble racing ahead of it, and ask the only question that finally matters. Is anyone actually going to compute something useful, or are we building the most sophisticated anticipation in the history of technology? If you spend enough time reading the week's dispatches from this field, you begin to notice something curious. The headlines shout about qubit counts and processor names, about who has the most, who has the fastest, who has the shiniest new chip. And yet, if you set those headlines aside and read the actual substance of what people are building, a rather different story assembles itself. The deep current beneath all this noise is not really about accumulation at all. It is about borrowing. The quantum world, having spent 2 decades insisting on its own exotic uniqueness, is quietly learning to speak the language of classical computing. Consider what it means to build vibrating quantum RAM. A group in Zurich has taken superconducting qubits and married them to mechanical resonators, tiny vibrations, actual physical oscillations, in order to separate the part of the machine that processes information from the part that stores it. Now that distinction, processor over here, memory over there, is the oldest architectural idea in classical computing. It is the fundamental division of labor that made the modern computer possible. And here it is, resurfacing in the quantum realm, not as an accident, but as a design principle. Someone looked at the beautiful, fragile mess of quantum hardware and said, what this needs is a proper filing system. You see the same borrowing elsewhere, and once you notice it, you cannot stop noticing it. A hardware developer demonstrates that you can shuttle electrons across superfluid helium using a commercial silicon control chip, the very same CMOS technology that runs the laptop on which I am no doubt being edited. Another team fabricates an 8-qubit array on a 300mm foundry wafer, the standard workhorse dimension of the semiconductor industry. The message is unmistakable. The exotic quantum object is being coaxed, wherever possible, onto the existing rails of classical manufacturing. Nobody wants to reinvent the entire industrial base of the 20th century if they can help it. So the deep current runs toward compatibility, toward making the strange thing fit inside the machinery we already know how to build at scale. But the borrowing goes deeper than hardware. It reaches into how these systems are controlled and even conceived. There is work using a reinforcement learning agent, a piece of machine learning, of all things, to stabilize logical qubits in real time, continuously calibrating and correcting errors while the computation is actually running. Think about the strangeness of that arrangement. The single hardest problem in this field, keeping quantum information alive long enough to be useful, is being handed to a self-teaching classical algorithm that learns the personality of the machine and babysits it moment by moment. And then, more startling still, there is the effort to project quantum operators, the mathematical objects that describe what a quantum circuit does, directly into the latent space of a large language model, treating these operations as though they were images to be recognized. The quantum and the classical AI are not merely coexisting, they are being fused at the level of representation. Now, why is this happening? One could tell a cynical story that everyone is simply chasing the gravity of the moment, bolting the word AI onto whatever they were already doing, and there is surely a little of that. But I think the honest reading is more interesting. The field has grown up enough to abandon a certain adolescent purity. For years, the dream was of a self-contained quantum machine, a magnificent standalone oracle. What is emerging instead is something humbler and far more plausible. The quantum processor as a specialized organ inside a larger classical body. Notice that a traptine machine is being wired into a South Korean AI data center. Notice that an analytics platform treats quantum computing as merely a downstream step in a hybrid workflow, doing the heavy verification on classical hardware first. The quantum computer is being demoted, if you like, from messiah to co-processor. And that demotion is precisely the sign of maturity. There is even a telling shift in ambition. The funding calls no longer fixate on the distant fantasy of the million-qubit machine. They ask instead for algorithms and error mitigation layers that squeeze value out of the imperfect, early, fault-tolerant devices we can actually build now. The horizon has moved closer, and it has become more honest. The design automation tools reflect the same turn, away from idealized, clean approximations of error toward simulations rooted in the messy physics of real hardware. So the deep current is not a wave of quantum triumph washing over the classical world. It is very nearly the opposite. It is the classical world, its architectures, its foundries, its control theory, its machine learning, its modest engineering pragmatism reaching into the quantum domain and domesticating it. The revolution, when it comes, will not arrive as a stranger. It will arrive wearing the clothes we already own. And in the third part of our conversation, I want to ask what that quiet domestication costs us and what it might quietly promise. If we've spent our earlier time together walking through the machinery, the electrons skating across superfluid helium, the mechanical resonators humming as quantum memory, the reinforcement learning agent quietly tuning error correction while a processor runs, then now is the moment to step back and ask the more impertinent question. Not does it work, but what does it mean that it works this way? Because the second-order implications of a field are rarely found in the press releases. They hide in the shape of the thing, in what the technology quietly assumes, and in what it quietly forecloses. Consider first the most striking convergence across everything we've surveyed, the borrowing of the classical world's own architecture. When researchers separate quantum processing from quantum memory and call the memory RAM, they are not merely being cute. They are importing a mental model, the von Neumann division of labor, that governs 70 years of computing. And when a language model is taught to treat a unitary operator as though it were an image, mapping mathematics into a latent space built for pictures and prose, we are watching the same instinct, bend the strange new thing into the grammar of the familiar. This is enormously productive. It is also, I'd suggest, the moment to keep one eyebrow raised. Every metaphor is a loan, and loans carry interest. The history of technology is littered with fields that mistook their scaffolding for their structure, that assumed, because the new machine resembled the old one, it must eventually behave like it. The thing to watch is whether these classical analogies remain useful crutches or quietly become intellectual cages, steering an entire generation of engineers toward architectures that are legible to us rather than natural to the physics. The second implication is subtler, and it concerns where the field has decided to point its attention. Notice the deliberate turn away from the mythical million-qubit machine and toward early fault-tolerant algorithms, error mitigation layers, enterprise use cases you could plausibly run this decade. There is a quiet maturity in that. It's the difference between a field that promises the moon and a field that has learned to sell you a very good telescope. But there's a second-order effect worth naming. When funding, competitions, and corporate calls all orient toward the immediately useful, they shape which problems get talent and which get patience. The distant, unglamorous foundational questions, the ones that don't fit inside a 2-year grant window, risk being orphaned. Progress that looks like acceleration from the outside can, from the inside, be a narrowing. Watch then not just what the field builds, but what it stops building and who is left holding the long problems. Third, and I think most consequential for the ordinary person who will never touch a dilution refrigerator, the cryptography story. We saw post-quantum cryptography being embedded directly into silicon, commercial accords to bake quantum-resistant methods into the hardware itself, seed rounds funding companies whose entire purpose is to help enterprises discover what encryption they even have. This is the part of the quantum revolution that arrives before the quantum computers do. The threat is theoretical. The response is already being poured into chips and cloud platforms. That inversion defending against a machine that does not yet exist at scale tells you something profound about how infrastructure ages. Data harvested today can be decrypted tomorrow. So the second-order implication is a peculiar temporal anxiety. We are being asked to secure the present against the future, and the market for that anxiety is, quite visibly, booming. When the security scaffolding races ahead of the threat, watch whether it hardens into genuine resilience or merely into a compliance ritual, a box ticked, a posture assumed. And fourth, the geography. Amsterdam funds rebranding and scaling, German consortia building trustworthy control planes, Shanghai's sovereign-backed capital pouring into photonic sensing, Korean data centers wiring in trapped ions. a Canadian firm planting itself in upstate New York's semiconductor corridor. This is not one field, it is many national ambitions wearing the same lab coat. The second-order implication is that quantum computing is becoming an instrument of industrial sovereignty, a way for states to claim a stake in the next substrate of power. That means the technical questions and the geopolitical ones are now inseparable, and pretending otherwise is a kind of naivety. So what does it all mean? I'd offer this. We are watching a field pass out of pure physics and into engineering, economics, and statecraft all at once. And the tell is that the exciting news is no longer only about qubits. It's about memory hierarchies and marketing officers, government affairs and seed rounds. That is what maturation looks like, unglamorous, plural, entangled with money and power. The signal ahead, if you want one, is this: stop watching for the single breakthrough machine. Watch instead for the assumptions hardening into infrastructure, because those are the things we will find it hardest later to unbuild. That's the signal for today. The noise will keep coming, we'll keep finding what's underneath it. This has been Signal Ahead with Alfred. Until next time.